Hey, AP Chemistry, this is going to be going over your Unit 1 test. Keep in mind that there are different versions of the test, so I'm going over one. First question I have is the last energy of a salt. Which again, a salt is just an ionic compound, is related to the energy required to separate the ions. For which of the following pairs of ions is the energy that is required to separate the largest? We went over this in class where the first thing you need to be looking for is the largest charge product. So plus twos and minus twos, which means it's got to be one of these two options right here because there's greater attraction. Second thing you need to look for, however, is the smaller they are, the closer they're together. So not only are they greatly attracted, but they're also close together, which means the Mg plus 2 and the O minus 2 would be the best option for this question. Again, don't be alarmed that it says 2 plus instead of plus 2. Both ways to write it are deemed acceptable. Next question I have here is a free response. How do I identify element J? What I need to do is look for a jump in the periodic table. Here I go from roughly 600 to 1800. That's not that big of a change. Here is an 1800 to 2700, not that big of a change. But then all of a sudden, I go from a little under 3,000 to over 11,000. That's an 8,000 kilojoules per mole jump. That's a big jump. That tells me that this element is able to lose 3 electrons fairly easily, but that fourth is really, really difficult. And if you can lose 3 electrons very easily, odds are you are in that third group right here. And since I told you that it's in the same period as sulfur, this would have to be aluminum for this particular element. So again, how does that data help you identify? That's what I just spoke of. You're looking for that big jump, that significant change, because after it loses its valence electrons, that next inner shell would be much more difficult to lose. As for number 2, this was just meant to give you a hopefully straightforward question of naming that. If I picked aluminum for number 1, how about AlCl3? AlF3, AlN. These are all good options. Looking at the mass spec graph, again, what you notice is that the average atomic mass is between 90 and 94. So again, I get out my periodic table and I look for something between 90 and 94. There's only 2 options on my periodic table, zirconium and niobium, when I look at this. Now, I only gave you one of those 2 options, so it makes this problem a little bit easier. Again, do not confuse this with atomic number, like 90, because that's when you're getting into the thorium and uranium type answers instead. So this mass spectroscopy graph showing the average atomic mass, not the number of protons. Another graph, photoelectron spectra. 1s2, 2s2, 2p3, because it goes up to the 3rd spot. And if I look at what's going to be 2p3, that would land on nitrogen. Then as for the best explanation for the difference between the far left peak, that's the 1s2, and the middle peak, the 2s2, peak 1 electrons have a greater coulombic attraction because they're closer to the nucleus. They certainly wouldn't have greater shielding because there's no shell of electrons between them. It's not a matter of the number of electrons. And repulsion wouldn't make sense either. Here's one of the main questions the students got wrong. Electron configuration for a transition metal ion. On my sheet of paper here, I have regular titanium's shorthand notation. What you were taught is that you lose from the outermost shell first. That means these 2 electrons will be gone. That's what you needed to identify when you did this. And as you can see then, right here would be your response. Next question that was tricky. This is dealing with that composition of mixtures problem that was in the review that I gave you as well. If you have 5-gram sample containing XCl2 and XF2, but there's a greater amount of XCl2, what would be true about that? Here's my thought process. Since Cl2 has a larger mass than F2, the percent composition of the non-metal is going to be greater in a sample that's this. That, on the flip side, means the percent composition of the metal, the X, will be less. And that's what I'm going to get into here when I say if more of the mass is due to XCl2, then there must be less X present in that 5-gram sample. So if I go back to my options here, you should be able to see, again, have a smaller mass of X. Interstitial is in between. So this right here is just substitutional. This is replacing those atoms in between interstitial. This problem had a lot of issues on it, unfortunately. A lot of people answered something like the MgF2. And I'm guessing what they're thinking is F2 is covalently bonded together. But if that were the case, it wouldn't even ionically bond to magnesium then. What you needed to recognize was that ammonium is a polyatomic ion. And with that, I actually drew out the Lewis structure to show here's the covalent bonds, but then here is the ionic as well. So this was just knowing your ammonium polyatomic ion and certainly recognizing, so here's your answer, certainly recognizing that the F2 does not covalently bond together. This graph was, again, on, among other things, the AP Classroom I went over this with. And this is almost the same graph because right here is your big dip for your N2. Why do I know that this dip on the bottom is N2? Because nitrogen is triple bonded to itself. Therefore, it's the strongest bond, the greatest amount of potential energy stored within those bonds. So now you see that these other two dips are pretty similar to one another. However, if I'm asking which one represents oxygen, not only should it be higher up because it's less energy, but oxygen being in the second shell, second period, rather than hydrogen being in the first period, means it's got a larger internuclear distance. So it should be skewed slightly to the right. And actually in the AP Classroom problem, it was just comparing nitrogen to oxygen. So when I give you these review problems, hopefully you can take that to heart and actually work on them. Formal charge, if I look at the carbon again, carbon typically has 4 electrons directly around it, but notice here it has 4 of unbonded electrons plus 2 more from the bonds, so it has 6 directly around it. That must mean it has a -2 formal charge. It, in essence, gained 2 electrons. Here is probably the next problem that gave people a lot of difficulty, is comparing CF4 to SF4. Here's the Lewis structure for each of them. And this is where I told you you did not have to submit anything, however, have a scrap sheet of paper available. And why did I bring that up? Because you wanted to draw these things out. This right here is in a tetrahedral position. So what you can see in this first tetrahedral molecule is it's perfectly symmetrical. Doesn't matter which way you cut it, it is the same. This is nonpolar covalent. All the dipoles cancel each other out. Same can't be said for the sulfur tetrafluoride because of the pair of electrons. I suppose if I split it this way, it would work out, but not if I go this way. And that's what you needed to notice on this problem, is that sulfur tetrafluoride is going to have that dipole moment. So again, identify which are polar, support your claim with reasoning. We had to talk about that idea of symmetry or that unbonded pair of electrons. Hybridization for the CF4 is sp3 hybridized. It had 4 domains. Lastly was a mole conversion. Most people are fine with that, although some people struggled with the typing in, which is a little odd because all you'd have to do is 46.58 grams. I would start a conversion, and I'd have 1 mole divided by whatever is the molar mass, and then close your parentheses equals. So a lot of people struggled with how they showed their work for that, which was a little odd. Last problem. This is a percent composition problem. Okay, notice a lot of these unknowns are given to you. So what I would do with this problem is realize that the formula is MCl3. Chlorine I know, times 3, here's the molar mass of chlorine. I would divide it by its percent in order to find the total mass. So this is the total molar mass. Now, if I know the total molar mass and I know the mass due to chlorine, I subtract the two, and I get 55.85. Again, I'm curious if most people answered aluminum simply because they saw, hey, it's a +3 and let's answer this. But then why was this number on there as well? Okay, so that was a quick recap of one of the tests, but all of them were in a similar format and similar problem solving as well. If you have any questions, let me know.